So first, in the last two sessions, we completed two methods known as a bisection and regular falsi. And the purpose of this method is to get the root of algebraic and transcendental equation. Okay. So just our aim is to get the roots of the equation by a numerical, by means approximate root, not necessary that it is exact root. We are just finding the approximate root. So a quick formula just I'm not going the method. Can anyone tell me what is the formula of bisection method, iteration formula?
A plus B by 2.
A plus B by 2.
Okay, a plus b upon 2, that's a good. So this is generally xn, nth iteration is given by a plus b upon 2. So every time we use this formula to bisect the interval, and we'll continue with the method. But the most important thing, method starts with the two initial points a and b, where f of a and f of b have the opposite sign. Now the formula for regular falsi.
AFB
A
minus
into
F
A
minus
f
upon
B
of
F
b,
plus F
b
by
f of a
F
upon,
of B minus F of A.
correct, f of b minus f of a, correct. So it is xn, that is nth iteration. So it may be first, second, third, anyone. So first we want again two initial point a and b, where f of a and f of b have the opposite sign. Generally these a and b are the two nearest integer. Okay, they are two nearest integer, so that we get a less number of iteration. If we not select two nearest integer, the problem is we require we may face a more number of iteration there. So that's the problem. Because of that, we select the two nearest integer. So the formula is simple: a f of b minus b f of a upon f of b minus f of a. It is based on the equation of a straight line, and that is the equation of the chord joining the points a f of a and b f of b. So mainly that chord, or is it second said? Okay, we'll come to that. Mainly it is chord which join that points. So there are two names. Sometimes it is referred as a regular falsi, or sometimes it is referred as a false position method. Remember, both are the same method there. Okay. So that about the two methods we finished in the first two sessions. Now today is the last session on this algebraic equation. So there is one more method in our syllabus, and that is the most important method, known as a Newton-Raphson method. If you observe this Newton-Raphson method, this is the most important method, because out of 5 times, 3 to 4 times the question is asked on Newton-Raphson only. Okay, why that is? First of all, this is the more accurate method, or it is a fast convergent method, okay, than the first two method there. So all the three methods have the same requirement. The initial requirement is the same. That is, we are selecting the points a and b so that f of a and f of b have the opposite sign. So this is the important thing that we require in all the three methods. Then only we'll start iteration. Okay. So once we get that a and b in the bisection, already we've seen this is our formula. In regular falsi, this is the formula that you should remember. Now in Newton-Raphson method, the formula is actually based on a single point only, because you will observe xn plus 1 depends on xn only. So this xn is generally b. We take xn equal to b always. That is the end point of the interval. So suppose the root exists in the interval a b. So for uniformity, actually I'm not saying that you are not getting the root with a. Yes, you can get the root with a also. If you take x0 equal to a, then also you can get root, but probably you may face more number of iteration there. So remember, every time we are going to fix that xn is equal to b only. So xn plus 1 is equal to b minus f of b minus f dash of b. Okay, so you can say the formula may look like this: xn plus 1 is equal to b minus f of b upon f dash of b. So there is one more thing that we require here, that's a derivative of the function. So previously we just have f of b. Nowhere there is a calculus involved. So we don't want the derivative of the functions in bisection and the false position. But in Newton-Raphson, we have this derivative that we require. Remember, in Newton-Raphson, actually we are approximating the root by a tangent. We are drawing a tangent at a point x equal to b. So we have a curve. We have curve y equal to fx. For that curve, we have the point x equal to b. At the point x equal to b, if you draw a tangent to that curve, and wherever that tangent intersect with x-axis, that is our first approximate route. So every time we are approximating the route by a tangent. If you want the detail of a derivation of these methods like false position and Newton-Raphson method, you can refer the notes that I already shared with you. Okay, that Word file or PDF file there, or you can go through the textbook also. Derivations will not come in the exam. Okay, any doubt in the formula first? Is there any doubt in the formula or method?
No, sir.
No, sir.
Good. So come to the questions now, numericals here. So the first example that we have, use a Newton-Raphson method to find a real root of this equation. Okay, correct up to 4 decimal places. Now there are two ways of the function this logarithmic function appears. Sometimes the function is written like this, log x. Sometimes it is referred as ln x, and sometimes it is referred as log x at the base a. So can anyone tell me what is the difference of all these notations? Yes, just I will ask particular because many of you are doing a group chatting now like that. When I ask a question, someone should answer. Like Piyush, yes.
Yes, sir.
I'm asking what is the difference between these three notations?
In log x, the base is 10, and
Okay.
in ln, the base is e, and
Okay.
the log a, the base is already given.
Yeah, good, very good. So this is a general thing. Remember, whenever log x is written, actually generally it is assumed that base is a 10. But in mathematics, there is a common habit becomes now. Whenever log x or ln x is written, both are considered as a natural log only. So remember, log x and ln x are same. Whenever the examiner or anyone want to specify you the base, so that time it is given like this, log x at the base 10. Okay, so generally actually in generally log is used for the base 10, but remember in mathematics, even though log x is written, only log x is written, it is ln x only. This is ln x only. Okay, don't confuse, it is not base 10 there. So whenever anyone want to specify the base, it is given in this form. So like log x at the base a, like log x at the base 10. Okay, so this is the first important thing you should know, that someone is on the chat. Is my voice is not clear?
No, sir, it's clear.
Okay, so Neil, you have some
Clear.
problem then. Okay. Yes, differences in respective bases, correct. So that is the first thing that you should know the notations. Okay. Now, just a minute. So this is the important thing that you should remember. Now, whenever log x appear or ln x appear in the question, remember you have to use a natural log for calculation purpose. Okay, so for that you have to press ln tab. There is a ln tab on a calculator that you have to press it. Okay, and to get ln, you can see there on calculator. There is a separate tab. Log x and ln tab, they are near to each other. So just press ln tab to get a natural log whenever you have log x and ln x only. But whenever log x at the base 10 is written, you have to press log tab for calculation purpose. I hope it is clear. Okay.
Sir,
Yes.
Okay, good. So
yes, sir.
remember there are these. Yes.
Sir, for calculation purpose, can we convert the question of log base 10 to the natural log by
Yes,
dividing by
yes, yes,
20?
yes, you can. But you should write
Okay.
that log x at the base 10 is ln x upon
Yeah,
ln
yeah.
10. ln x upon ln 10. That is the formula. Is that correct? Change of base formula, you can use it, and then you can proceed. Actually, when you have to differentiate, na, you have to do that only, because derivative, we know the derivative of log x is 1 by x, but that is only for natural log. That is not for base 10 there. So if you write the derivative of log x at the base 10 as only
Sir,
1 by x, you are wrong then. Okay, I hope.
yes, I was
Yeah.
solving from this question from Newton-Raphson method, and I got that confusion. So,
Okay, 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 good. No issue. So that thing you should keep in mind that yes, you can convert any base to the natural log with the change of base formula, and you can do that. Correct. So there are two cautions that you have to do in these algebraic methods. Whenever trigonometric term appear, which mode you should use of a calculator?
The radian mode.
Radian mode. And whenever ln x or log x appear, you should use ln. Okay, ln tab of a calculator. That are the two cautions that you should keep in mind. Okay. Now let me find the interval in which that root exists. So first we should write this equation in fx form. So what is our fx? Yes, anyone? What is the fx?
X log x minus 1.2.
Correct. X log x minus 1.2. So this 1.2 should be taken on one side because our fx is always in the form fx equal to 0. Okay, then only we get root of that fx now. So the first thing we
Yes.
assume, let fx is x log x at the base 10 minus 1.2, that is fx. Now what is f of 0? Yes, anyone calculated? What is f of 0?
Minus
So
1.2.
not defined.
Not able to? I'm asking f of 0. Log 0 is not defined, is it?
Yes, sir.
Log 0 is undefined. Okay, so
Minus
you
1.2.
can proceed to 1 then. Next integer then, f of 1.
So minus 0.5979.
Okay, let me check. So f of 1 is a minus 1.2 only.
Yes, sir, minus
Log 1 is
1.2.
Sorry, sir,
exists. Okay, minus
I
1.
told you the f of 2, sir.
Okay, f of 2. Yeah. So next is f of 2. F of 1 is negative. You will observe minus 1.2. F of 2 is also negative, minus 0.59. So we have to till continue this till we get a positive value now, so that we can conclude that root exists in that interval. So f of 1 is negative, f of 2 is a negative, f of 3. Yes, f of 3 is a positive, is it? I hope you are doing calculation on calculator. Okay.
Yes, sir.
Yes.
So we can conclude here the root exists in the interval 2, 3. Okay. So that is the first and most important thing for all the three methods. Our aim is to first search the interval. Okay. Our aim is to first search the interval. That interval must be the two nearest integer. Boundaries should be the two nearest integer in which that root exists there. Now we got the interval 2, 3. So what should be the initial approximation x0? What is x0 for Newton-Raphson? First approximate root will start with one iteration there. Yes, anyone? What is x0?
3.
It is a 3. 3 is a correct answer. Good. So generally from the interval AB, we select B as initial approximate root. So x0, let x0 is a 3. Remember in the textbook, they once they observed that the root exists in the interval 2 3 for some examples the author done like he calculated f of 2.5 also. Suppose f of 2.5 comes a positive, then the root exists between 2 and 2.5 is written, and then x0 is taken as 2.5. That is also correct. I am not saying it is wrong. Okay, so choice is yours, but the minimum you should take a nearest integer, and you can reduce that interval if you want. That is your choice. You can calculate 2 and 2.5, f of 2 and f of 2.5 after this, and then you can say the root exists in 2 to 2.5. Is it clear?
Yes, sir.
So that is your choice at the end.
Yes, sir.
So this is the I started with only 2 3. I fixed that nearest integer only. So you'll observe the first thing that we have, that fx is this one. Fx is x log x minus 1.2. Now by change of base formula, log x at the base 10 can be written as ln x upon ln 10, or log x upon log 10. Is that clear? This is the change of base formula to write log x. What is this? This fx is written here.
Yes, sir.
Okay. Now let me differentiate f dash x. Now remember ln 10 is a constant that remain as it is in the denominator. We have to write the derivative of x into ln x or x into log x. So just we use the product rule. First into derivative of second, that is x into 1 by x. plus ln x into 1. So that is f dash x. So and derivative of minus 1.2 is a 0. Is that clear? This is f dash x.
Yes, sir.
Okay, good. So why we calculated f dash x? Because our formula of Newton-Raphson says n plus 1 iteration, that is xn plus 1, is equal to xn minus f of xn upon f dash xn. So we require the value of fx as well as f dash x. So now we are going to write x1 equal to that b minus f of b upon f dash of b. Okay. So let me see here. So this is the first iteration, n equal to 0. X0 is taken as a b. What is b? B is 3 here. Okay. So this is 3. So f of xn is calculated. So you can replace f of x by 3 here, f of 3, that is already we calculated. F dash of f dash of 3 also calculated, f dash of 3, and that is written here. Now x1, this is the x1 equal to x0 minus f of x0 upon f dash x0. So 3 minus this number divided by this number is the x1. I hope you are getting how the x1 is calculated. Any doubt?
Yes, sir.
Okay. And now in the next step, this is x1 come here. This is n equal to 1. So x1 is here. With the help of x1, we calculated f of x1, f dash of x1, and we calculated x2. And we'll proceed. So you'll observe this is the fast convergent method. Remember in final exam also, maximum 2 to 3 iteration you have to do it for Newton-Raphson method. Newton-Raphson method generally never you require more than 2 iteration, I will say. Means you have x0, you have x1 and x2 only. So you will get a very good approximate root up to 4 decimal places. Not only 2, it is 4. You will observe in bisection or regular Falsey method, root is converging by decimal, 1 decimal. But here you will observe at first step only 2 decimals directly goes correct, and then 4 decimal. So it is we say 2 decimal. So convergence rate is a faster. Simply I can say convergence rate is a faster of the Newton-Raphson method. So quickly in minimum number of iteration we get a better root than the previous two methods there. So after second iteration, this is the root with correct up to 4 decimal places. Final exam also, you can do the maximum 2 iteration. That is enough there. Got it? Any doubt?
No, sir.
No, sir.
No, sir.
If you see in the question, I think in the question, stopping criteria is given or not given? Let me check. So 4 decimal places is written. Yeah, stopping criteria is 4 decimal places. So when we stop the iteration, when all the 4 decimals start repeating, you will observe 7406, 7406. As it is repeated, we stop the iteration. And generally, 4 decimals correct becomes in second iteration always there. Okay. So next question is on the screen. Using Newton's method, find the real root of x e raised to x equal to 2 correct to 3 decimal places. So what is fx here?
X
E,
is raised to x
e
minus
raised
2.
to x minus
Yes, minus 2. So we should take these terms on one side, correct. So fx is x e raised to x minus 2. Now what is f of 0?
Minus 2.
-2.
Minus 2. Okay, correct. F of 1? Can you check? 0.7182 is it?
Yes, sir.
So we got a nearest integer now. They are in 0 and 1 only. So we can say the root exists in the interval 0, 1. Root exists in the interval 0, 1. So let x0 is equal to b as usual. We'll take x0 equal to 1. We take a and continue. So this middle cells are empty that you have to fill up. I not written here. So you have to write f dash of x1. You have to write f of x1. Sorry, here is f dash of x0. So f dash x0, f dash of x1 and f dash of x2, all that values are not written anywhere. So I not written f dash x itself. What is f dash x first? Yes, anyone?
x
Sir,
a to the
x
e to the
in
power x
bracket 1 minus
minus e
e
dx.
minus e raised to x.
Okay, so in short, it is a x plus 1 e raised to x, x plus 1 into e raised to x. Okay.
Yes, sir.
So that is f dash x. So you require that f dash x, and then that in with that f dash x, you can calculate f dash of x0 and so on. So you'll observe in 2 iterations again, the answer got correct up to 3 decimal places now. 3 decimal places. Okay. So this is the answer correct up to 3 decimal places. One more last important thing. Remember, whenever the final answer is suppose 0.852, 0.852 is the final answer. By chance, in the exam, you got the answer 0.850 or 851 or 853. So roughly that is considered correct and you get a full marks there. But if you have too much variation, say this is the 0.852 is the correct answer and you are getting 0.840. 0.840 is too much away from that. So few marks deducted there. And suppose 0.7 you are writing the answer, you completely wrong. Probably you get 1.5 mark there. Got it? So as they are approximate answers, you should be more closer to the correct answer there. Okay. So here is f dash x is written. So that f dash x are used. Third example. What is the best part in this question? Yes, anyone? What is the best part? What is the best part of this example?
Near 0.6.
Near 0.6 is a given. That means x0 is given. So there is no need to calculate that interval AB. Now, there is no get to start with the interval AB, that is f of A and f of B positive negative. Directly we given, we have to find the root which is near to the 0.6. So we take that as a x0. x0 is a 0.6. Another important thing, yes, another important thing from this equation.
So,
Pardon?
Sir, x should be in radian, cosx.
Yes, Chirag, correct. So we should convert. We should use a radian mode of a calculator as trigonometric term appeared there. Okay, this trigonometric term appeared in fx, so we should use a radian mode. So calculation will go like this. The first fx is given 3x minus cos x minus 1. F dash x is calculated. This is a formula. Xn plus 1 equal to xn minus f of xn upon f dash of xn. X0 is given, so x1 calculated, then x2 calculated, and this is the answer after second iteration because it start repeating up to 4 decimal places. So after second iteration, the answer is correct up to 4 decimal places. Remember, this is another way of giving a solution. It is not a table form. You'll observe previous 2 solution I shown in table form. This is in descriptive form. So you can write in any of the way. Both are correct. If anyone have a doubt here, yes, you can ask. No doubt?
No, sir.
Okay. So come to the last part of the Newton-Raphson, because Newton-Raphson have some these examples where we deduce some results for getting the nth root of the number. So these type of questions are also frequently asked in the final exam. This is the last type in the Newton-Raphson where we have to derive or we have to find the iterative formula to get a square root of n. And then we have to find out root of 41. Remember, you have the final answer with you already. What is the root 41? Yes, anyone? What is the root 41? You have to use a calculator definitely because
6.4.
6.4.
yes, 6.4031. So this one is the answer. You are going to get it only 6.4031. But you don't have to write directly the answer by calculator. Yes, you are using calculator only, but you have to do it by numerical method. Okay, you have to do it by a numerical method here. Even though some of you think it is a foolish thing that already calculator gives it. Why there is a need to calculate this? But remember, in program, if you don't know these numerical methods, you cannot do the programming first of all. Okay, and by that programming only, you because behind the calculator only these methods are running behind the screen, and you are getting these answers there. So you are coming to know this logic. What is the logic that is used for programming? That is actually you are learning here. Okay. And these topics are used later on in few subjects that you are going to learn in your upcoming semester, like AI and ML. Okay, whenever you are related to the artificial intelligence and machine learning subjects related to that, if any subject comes, and I think in new curriculum there are one or two subjects kept already like that. So you require a few topics from these, like numerical method as well as statistical method, that are important for AI and ML there. Okay, so we'll not go in the detail of the application right now. Just we are focusing on mathematics part here. Okay, come to the part here. Our aim is to get square root of n. So can anyone tell me what should be our fx? What should be the
X
fx?
square
So
minus
x square minus n equals to 0.
Very good. So this is the main part. Equation is not given. We have to derive it. So to get that equation, yes, we start with let x is a root n. So x square minus n is 0. So this is our fx. Fx is x square minus n. So fx is x square minus n. So f dash x, yes, 2x. Now we have that formula xn plus 1 equal to xn minus f of xn upon f dash xn. So by Newton-Raphson method, xn plus 1 is xn minus f of xn upon f dash of xn. Now we have to just first write a general formula. So because the question is obtain iteration formula first and then use that iteration formula to get a root of 41. So xn will keep as it is. What is f of xn? Anyone? What is f of xn? Xn square minus capital N, is it? F of xn, because we replace x by xn everywhere. So f of xn is xn square minus capital N, and f dash of xn is the 2xn. So if you replace these values, you will get this one. Actually, instead of xn plus 1, it is written in k n. Instead of xn plus 1, xk plus 1 is written. Both are okay. If you write in final exam as xn plus 1, don't worry, that is also correct. So xn plus 1 is xn minus xn square minus n upon 2xn. Is it clear?
Yes, sir.
Yes, sir.
So yes, anyone have a doubt there? No? No.
No,
Okay.
sir.
Okay. So this is the iteration formula. You can. Yeah. Yes, Tejas.
I said no, sir.
No.
No doubt.
Okay. Okay. Yeah. So this is the iteration formula for getting the root, for the root of the n, root of this capital number n. But sometimes you can keep this as iteration formula also, and you can keep this as final answer. Or if we want, we can simplify. What is the simplification possible? Yes, you can cross multiply. That is one way is possible. Or you can take separate division here. That is also possible. So you can keep any of the iteration formula here. The separate division is done. Xk square upon 2xk is xk upon 2. So this is the first term. Minus n upon 2x. Minus minus plus. Plus n upon. So this way it is written. So this formula is written in little simplified form. But if you are not interested to do these two steps, that is okay. You can just give this as equation 1, and that is your final iteration formula without simplification. Okay. So that about the first part of the question. We got an iterative formula. Right now I am taken this as an iterative formula for getting a square root of that number n. Come to the next part. The next part we want a root of 41 now. Root of 41. So to get root of 41, can anyone tell me what should be x0? What should be initial approximate root for 41?
So 7.
Okay, 7 is the answer. Good. Both way it is correct. So right now you already know it is a 6.40 is the answer on calculator you checked. So you can take x0 equal to 7. That is the best choice. Okay. Or you can take x0 equal to 6 also. Okay. Generally I said yes in the interval AB we have to take it as a upper part, but here we not checked whether it is positive or negative. Otherwise you have to see what is f of 6. F of 6 is coming negative. Yes, correct. Probably because it is 36 minus 41. but f of 7 is a positive, and the root exists in that interval AB there, correct? So you can take x0 equal to 6 or x0 equal to 7. Both are correct. You will get the answer. Don't worry. Okay. So I think I taken here it as a 6 there, because 6.40 is there and the root exists in 6 to 7. 0.40 indicates it is near to the 6. It is closer to the 6. As it is closer to the 6, so 6 is taken. But by 7 also you will get it. Don't worry. And here is the final answer. So x1 is calculated here. How x1 is calculated? With this formula. x1 is 1 by 2 x0 plus n upon x0. So what is x0? x0 is a 6. Capital N is 41. 41 upon 6. So here is written, and that is a x1, then x2 and x3. You will observe this answer you got correct up to 4 decimal places. Any doubt?
No, sir.
Okay. So a last question then, exactly similar to this, only there is a small difference. Instead of root n, the formula may be the nth root or pth root of that n. We have to derive formula for pth root of n, and then we'll check what is the question. Come to the last question then. Here is that last question. Obtain the iteration formula for pth root of n, and then we have to find cube root of 10. Cube root of 10, correct to the 3 decimal places. You'll observe we have to find pth root of n. So let x equal to n raised to capital 1 by p. X is pth root of capital N. So x raised to p is n. So I hope you are getting what is fx. Fx is x raised to p minus capital N. Is it okay?
Yes, sir.
So f dash x become p into x raised to p minus 1. F dash x is a p into x raised to p minus 1. That is f dash x. And exactly similar way it is completed. Then the formula is written. So this is the iterative formula that we are going to use it for this calculation purpose here. And you will observe cube root of 10. If you see on the calculator first, what is the cube root of 10 you will get on calci? 10 raised to 1 slash 3.
2.15.
2.15. Okay, good. And because of that, x0 is taken as a 2. X0 is taken as 2. Now in this case, remember, in this case, if you take the x0 is taken as 2, if someone take x0 as 3, remember you have to do 5 to 6 iteration. Why? Because the root is a 2.15, 2.15, and this number is definitely closer to the 2 than 3. If you take x0 as 3, you may require 5 to 6 iteration there. So better to take x0 as a 2 only. But if you take x0 as 3, it's not wrong. You may have to do 5 to 6 iteration, maybe 4 iteration also, one more iteration only. So you tried that calculation with 3 and you'll come to know that how many iterations you have to do it. So that about our last method, Newton-Raphson method. So if I sum up our first article that we completed, okay, which is solving the algebraic and transcendental equation, solving algebraic and the transcendental equation. There are 3 methods that in our syllabus: bisection, regular falsi, and Newton-Raphson. Most important method is a Newton-Raphson, then regular falsi, and then bisection in reverse order. So that is the importance of the methods there. All the 3 methods are based on some initial approximation. So mainly we require some interval AB, which is nearest integers where the root exists, and then we start with iteration formula and we get approximate root, okay, up to certain decimal places or up to desired accuracy. Any doubt, anyone?